This lesson is about continuity. Continuity just means when a function does not break or have a hole in it, or something. Basically, you can draw the function without picking up your pencil. It's a good way that a lot of people say how to describe continuity. But maybe to tell you about continuity, it'd be best just to talk about what makes a function discontinuous. So there are three kinds of discontinuities. So here's the three kinds of discontinuities that I could think of offhand. So one of them would be a hole, and the other one would be an asymptote, and the other one would be a break. Now there could be others, but these three are really common. And there are two ways to describe discontinuity. Some say these are removable, and these are non-removable. So you can easily redefine a function so that there's not a hole. These two are not so easily redefined so that there's not a discontinuity. So that's why they call these removable and non-removable. And there are functions that have asymptotes very commonly are rational functions. And that would be like 1 over x. This is a rational function. They call it rational because of the root word ratio, rational. You notice in ratio that means a fraction or like a ratio of two numbers. So that's why they call these rational. These are the most common ones to have an asymptote. And asymptotes happen when the bottom or the denominator has a 0 in it that won't cancel. So 0 in the denominator that won't cancel. These have a 0 in the denominator that will cancel with the numerator. And I'll pause it and make some examples to show you what I mean. These are two rational functions, and we see that here when x equals -5, the bottom here is 0, and you remember you can never divide by 0, so that makes bad things happen. And that is what causes this function to have an asymptote, because this will never cancel with a 1. You would need an x plus 5 up here to cancel this x plus 5 out, so that means that this is an asymptote. Over here, we need to factor the bottom and the top. Top's already factored. Factoring the bottom gives you this, x squared minus 16, x squared plus 16. You'll remember that because this is a difference of squares. This one will refactor, x minus 4, x plus 4, and just bring down the x squared plus 16. So this is all just a rewritten form. Now we see that the x minus 4 will cancel, but these two will not. So since this canceled, there's a hole there. When this would have been 0 anyway, which would have been at x equals 4, because 4 minus 4 is 0. And these two will not cancel, so these make asymptotes at -4, and actually this is never 0. Because you can't square a number and add 16 to it and get 0, unless you're talking about imaginary numbers, which we're not. So if I wanted to describe the intervals that this function was continuous, you could just say it's continuous everywhere but these two numbers. And one way to do that is some shorthand I'm going to introduce, which is called interval notation. An interval notation is when you use parentheses or brackets or some variation of them to sort of bookend an interval. So if I say like 3 to 8, this would mean everywhere between 3 and 8, and I'm not going to include 8, but I am going to include 3. So that's how you do interval notation. Brackets are like the closed circle type thing on the number line. Parentheses are like the open circle type thing. So if I wanted to describe the intervals where g is continuous, I would say continuous on negative infinity all the way to -4. Notice I'm not going to include -4 because there's an asymptote there. can't include infinity anyway. That's just a figment of your imagination. This isn't a number. So we got -4 all the way to negative infinity. So on the number line it looks like this. And also from -4 to 4. And also, I guess I didn't need that end, from 4 to infinity. So these are the 3 intervals where this g function is continuous, because there are 2 spots where there's a break. So that means there are 3 intervals. That's how you tell an interval of continuity. Here's another function. This is called a piecewise function. It's called piecewise because there are 3 pieces, and you basically just use this piece if you're on this window, like on the x-axis, and you use this piece, which is a parabola. It's not the whole parabola though. We're just going to use a small chunk of the parabola between these x values, and then this is the line y equals 16. We'll use this line everywhere after an x value of 4. So basically this has a break at 3 possibly and a break at 4 possibly, and since we know that this is a linear equation, there's no breaks to the left side of 3 because the linear equations are continuous, and this is a parabola which is continuous, so we're continuous in between here, so on. So to check to see if we have a continuity at x equals 3, what we'll do is we'll put a 3 in here and put a 3 in here. See, because this is where the potential break is, between these two. There could be a gap between this line and this line. So we're checking 3 again because this says everywhere up to 3, and this says after 3 but stop at 4. So right here, f of x equals x minus 3. If I check f of 3, that'll be 3 minus 3, which is 0. And this is from the left, I guess I should left. And f of 3 from the other side is 3 squared, which is 9. And actually I shouldn't have put an equals here because this does not include 3. So this is only as you approach 3. The actual value, this is or equal to 3, so if I'm only using this function, then f of 3 is 9, not 0. And we see that there's a break here. So as x approaches 3 from the left, my limit of f of x is 0. See, on a number line, I have, like, 1 and 2 and 3 and 4. And as I'm approaching 3 from this side, see how that's coming in from the left? That's stopping here. And then from the right, this is to the right side of 3, from the right looks like that. So that interval looks like this. Actually, that's an open circle, because this is not or equal to, and a closed circle here. So on this interval, I'm using x squared, so that would be the limit as x approaches 3 from the right, and that is 9. So you notice that these two aren't the same, so that means this function is discontinuous. And this is your new notation for the day. X approaches 3 from the left, and x approaches 3 from the right. Okay, let's check the other break. So the limit as x approaches 4 from the left would be to say use this one. You see how this is a better notation because I'm not including 4, I'm just saying push toward 4 from the left. So that would be 16. Plug a 4 in right here. And the limit as x approaches 4 from the right would be this interval. So that's always 16. You notice these are the same y value. And so what that means is the exact spot where this function ends, this function starts. And so I then could possibly have continuity. So I need to look at these two right here. And this would be continuous if both of these weren't holes. So if one of these, say this looked like this, then this function now becomes continuous at x equals 4. Because the exact y value where this one stops, fill in the circle, is the same y value where this one starts with an open circle, but since the circle was closed here, we have continuity there. If this green line wasn't here, even though this stops at a y value of 16 and this one starts at a y value of 16, since neither one of these was or equal to, we would still have a discontinuity. And actually, this is the textbook definition of continuity. Its textbook says when the limit from the left is equal to the limit from the right, and the function's value at that spot equals both of these limits. We'll call this A and this B. You got to check A, you got to check B. And if this equals A and B, both of these, then you know you have continuity if all three of these are true. So if we wanted to check f of 4, that would be this line right here. And yes, f of 4 is also 16, so these three are all the same number, so we do have continuity at 4. But remember, we didn't at 3. Because when you plug in a 3, you get a 0 here, and you get a 9 here. So this function stops at 0, this function picks up at 9, there's a break there.